This lecture is going to address Ohm's law and the power law. So first we'll look at some definitions, and then we'll look at both the Ohm's law, power law, and energy. When we speak, we often use just vague terms, and we talk about maybe somebody's height. We might say something like they're very short or they're very tall. But when we talk about units, we use units to describe exactly how tall someone is. We could use maybe feet. We could say that, hey, this person is actually 6 foot tall. Or we could use a different unit, say he's 72 inches tall. But either way, we're precisely quantifying how tall that person is. So for electrical terms, we have several different terms here. Of course, we've discussed many of these already. So resistance is the opposition of current flow. The units for resistance is in ohms, which we use the capital omega to, or the Greek letter omega as the unit symbol for ohms. And the resistance is actually based on the physical properties of that device or element within a circuit that we're concerned about. And so we have the resistance, we have rho, which is the resistivity depending on the property of the material, the length of the material divided by the cross-sectional area of the material. Current is the flow of charge. So officially current is the flow of charge, but in solid materials it's technically going to be the electrons that are actually moving. The units for current is amperes, and we use a capital letter to symbolize the unit ampere. Again, it's a capitalized because it's named after a scientist. So it's a proper noun. Voltage is the force that pushes those electrons or moves that charge. And so sometimes we refer to it as a potential difference or an electromotive force. This force is caused by the separation of positive charges and negative charges. So the more charge you have built up, then the more voltage that you have. So usually the units for this, we say volts, and again it's named after a scientist, so we use a capital V as the symbol for that unit. Power is an instantaneous energy, so it's basically the potential to do work. Okay, energy or work is force times the distance. So remember that voltage is an electric force, but we need to move those electrons. So when we have the force and we have the movement of electrons both, then we're actually doing work, which is force times distance. And so power is measured in watts. Again, that's after James Watts, so it's a capital W. And energy is the movement of that charge, again, and how fast effectively we're doing it, or how much force that we have moving it. And so the units for electrical energy, officially the units for energy or work is joules. So again, capital J because it's named after a scientist. But when we're talking about electrical energy specifically, we usually talk about either the watt hour or 1,000 watt hours or the kilowatt hour. So 1 joule, just for a reference, 1 joule is basically 277 microwatt hours. All right, so Ohm's law then defines the relationship between the voltage, the current, and the resistance. As the electromotive force, or the voltage, is increased, so if we increase this electromotive force, then the current will increase. Or if we decrease the amount of resistance, okay, so if we decrease the amount of resistance, the current is going to increase. So this little symbol here for voltage, current, and resistance is often kind of used to indicate the Ohm's law, because we have the three elements. And so if we're looking for the voltage, if we wanted to find the voltage, you kind of cover this up, and then you can say that you're looking for the voltage times, or the current is current times the resistance gives us the voltage. If we're looking for the current, okay, so if we're looking for the current, we cover up the current, and then we have that we're looking for the then we calculate the voltage divided by the resistance will give us that current. So this, you basically can like set your thumb over top of which element that you're looking for. So if you're looking for resistance, it's going to be voltage divided by current. So this little symbol makes it very easy. You can quickly sketch this out and then visually see whether you should be dividing or multiplying. All right, so the again, the electromotive force is the voltage. Okay. E, we use the symbol E. Sometimes you'll see an E up here for the voltage, but remember that the E represents a power source. Ohm's law applies whether you're talking about the power source or the voltage drop across a single resistance. So the term V indicates just a voltage anywhere within the electrical circuit, where E specifically is referring to a power source, a power supply, a battery. Okay. As the resistance increases, if we don't change the voltage and resistance increases, then the current will decrease. Right? Now the power law looks effectively exactly like the voltage law. So if we're looking for power, so if we wanted to find power, we would basically cover that up and we would calculate power as voltage times current. Remember that power is the instantaneous amount of energy available. So energy is over time in watt hours. How many hours have we had this much power? But power itself is instantaneous. So how much power do we have at this exact second? And that power is simply voltage times current. If we wanted to find the voltage but we knew the power, then we could divide the power by the current to give the voltage. If we wanted to find the current and we knew the power and the voltage, we cover up the current, so we take power divided by voltage. Now, since Ohm's law tells us that current times resistance is voltage, okay, we can actually calculate the power inside of a resistor by taking I squared times R. So remember that resistors, effectively what a resistor does is convert electrical energy into thermal energy. It converts that electrical energy into heat and makes that resistor hot. And so that's why we use the term of dissipated, because we're converting that electrical energy into thermal energy, and then that thermal energy is being released into the atmosphere, and so it's kind of lost. It's turned into heat, and we can maybe try to capture the heat, but effectively it's lost. All right, so again, energy is doing work. So energy is basically power times time. So we take wattage, kilowatts, times hours. All right. Okay. A joule, by the way, is in terms of seconds usually. So you would have to convert it to hours. That's why the joule value was so small. All right, so let's actually take a look at a simple circuit here. And with this simple circuit, we see that we have a power supply. This is actually the symbol of a battery here. And so it's supplying a voltage. Now, it doesn't specifically state it here, but the fact that this symbol is used, we know for a fact that this is a DC power supply or a DC battery. This is the ground symbol. The ground symbol is your reference point, and so at ground you're at 0 volts. That's your reference point. And so as you can see, as we go up through the battery, we're going up. See the positive, this longer one indicates a positive sign. So we're going up through the battery, we're going up 20 volts. Okay. And so this here is actually considered a node, and a node is the same voltage everywhere. So all along this is a conductor, and we already kind of talked about conductors do have resistance, but when we draw the circuit like this, we're assuming that this conductor is a perfect conductor and therefore has 0 resistance. So we know there's resistance there, but we're going to ignore the resistance in the conductor. This down here is also a conductor, so again we're going to ignore any resistance within there. All right, so using Ohm's law, again, using Ohm's law here, we know, looking at this circuit, since this is a perfect conductor, there's no voltage drop, there's no resistance here. So if there's no resistance, there's no voltage drop. And so the voltage of 20 volts over here is the voltage V1. So V1 is also going to be 20 volts. So therefore, using Ohm's law, we can find the current flowing through this resistor. Okay, and this is a series circuit. So there's current flowing out of the battery through the resistor and back into the battery. So the current is the same everywhere within a series circuit. And so we can calculate using Ohm's law. Now we don't know a resistance over here, but we know it's a power supply and it's got 20 volts. And so we know that we've got 20 volts over here. So we can therefore calculate the current I. All right, so we're going to cover up what we don't know, or what we want to find. We cover that up, and then we get that the voltage divided by resistance. So we get that I is the voltage divided by the resistance, which gives us, we have 20 volts divided by the resistance, which is 1 ohm. Okay, and the units of volts divided by ohms gives us amperes, so that gives us 20. And if we're going to put this in Blackboard, we need 3 significant digits, so it's going to be 20 amperes. So the answer for Blackboard then would be 20.0 ampere. So remember, we need to make sure that we leave a space between the number and the units. Okay? But this is how we calculate the current in a circuit. Now IS here, a lot of times since they're showing IS coming out of the battery, I would assume I sub S to imply that that is the supply current or the source current. You could also consider it the series current because it's the current in a series circuit. V1 is the voltage across resistor R1. So if you see here, we've got, this is resistor R1, and so this is the voltage drop across resistor R1. And so I would, a lot of times I might put like I1 because I1 indicates that's the current through resistor R1. Right, so this is just some common notation that we use. So if we look at a slightly more complicated circuit, in this case we actually have two resistors. So I have resistor R2 or R1 and resistor R2. So the voltage drop across resistor 1 is V1, and the voltage across resistor 2 is V2. Now each one of these are going to have a current flowing through them. So I'm going to have a current I1 and I'm going to have a current I2. Okay, so I1 is the current through resistor R1 and I2 is the current through R2. Now in this case it's a series circuit. So what that means is that the current coming out of this battery is going into resistor R1, it's coming out of resistor R1 into resistor R2, it's coming out of resistor R2 back into our supply. Alright, so remember the current is the same everywhere, so what that means is that the supply current IS, or the series current, is equal to the current I1, which is equal to the current I2. So these three currents are all the exact same current because it is a series circuit. So when we look at that then, since it's the same current, we have this resistance R1. So we have this resistor R1, so we have the current is got to flow through R1, resistor R1, but then it's also got to flow through resistor R2. So it's got to flow through both of these resistors. And so the total resistance, over here they have this RT. RT indicates the total resistance. The total resistance is the sum of both resistors. So now we have R total. So we have R total now is R1 plus R2 because the current has to flow through both resistors. So the total resistance then is the sum of both of these resistances. So now when we start talking about calculating the total supply current, okay, so I should have probably added over here that this current IS is also equal to the total current. Okay, so the total current I total, which is the supply current, which is also the current I1, which is also the current I2, because it's a series circuit. These, you know, in any way you reference these are exactly the same. So using Ohm's law, we can calculate this total current is equal to the supply voltage divided by the total resistance, which is going to be 20 volts divided by, this is now 2 ohms. The total resistance is 2 ohms. So divided by 2 ohms. And so therefore now our total current is 10.0 ampere. Okay. So again, when we put this into Blackboard, we need our 3 digits here. So we need these 3 digits. So it's 10.0 space and then capital A for ampere. So there's your answer in Blackboard. Alright, now since both of these are exactly the same resistance, since both of these are exactly the same resistance, then they're going to drop the same voltage. So we can kind of see that here. So if I say, well, what is the voltage V1? Well, V1 is equal to, Ohm's law tells us it's the current through the resistor R1, which is I1, times R1. But remember, I1 is the same as the total because it's a series circuit. Because it's a series circuit, that's the same. So we're going to have 10 amps times the resistance of 1 ohm, which is going to be 10 volts. Okay, 10.0 volts. All right, so just another reminder here that when you look at these values, like up here, when we come up here and we look at this 1 ohm, there's no decimal points here, but these are assumed to be exact values. Okay, so 1 ohm is considered an exact value, which means it's like 1.00000. It's like a very precise value. Alright, so obviously then, if we do the same thing for V2, right, so we can come in here and we can say V2 is equal to I2 times R2, but again, the current I2 is equal to the total current, which is equal to 10.0 amps times 1 ohm, which is equal to 10.0 volts. Alright, so what we see there then is, because we have these resistors, the resistors are exactly the same size, then we get each resistor is going to drop half. We got 2 resistors. Each resistor is going to drop half of the supply voltage. 2 resistors in series are going to split that voltage in half. Alright, so let's look at maybe just a slightly more complicated circuit. So this here is still a series circuit. So it's still a series circuit. And so we still have the same current everywhere. Right? So we still have that these currents are exactly the same everywhere because it's a series circuit. So we still have that the currents are exactly the same. But now we have that R2 is going to be 2 ohms. Okay, so therefore our total now is R1 plus R2, which is exactly what we had before. I don't know why it keeps popping a 0 up there on me, but okay, so our total is R1 plus R2, but now that is 1 ohm plus 2 ohms. So now our total is 3 ohms. So again, if we're going to put this into Blackboard, we're going to put 3.00. So we want 3 digits. So even though these are exact values, when we put it in Blackboard, we're going to assume that we calculated these values, even though it's summation. So we're going to do 3 significant digits. All right, and then you can put the omega symbol if you want. If you find it somewhere, you can copy it and paste it in there, but remember there should be a space here between them. Or you can just spell out ohms. Now, when you spell out ohms, you actually put a lowercase there when it's associated with a units. Yes, it's true that ohm is named after the scientist Ohm, but when you spell out the ohms, you would put a lowercase ohms there. So if we were going to put this in Blackboard, we could actually just put it right like this: 3.00 space ohms. You put ohms because there's more than one. So and even if you actually had 1.00 ohm, it would actually be 1.00 ohms because of the significant digits on here. Kind of implies that it's at least slightly more, even though in this case they're actually exactly 0. All right, so given that, then, right, we can calculate that the total current IT, so we can then say that IT now is equal to the supply voltage of 20 volts divided by the total resistance. Okay, so that's going to be 20, which again is an exact value because that was the supplied value. So 20 volts divided by 3 ohms. And so then we can pop over to our calculator. So we'll take 20 divided by 3, right, which gives us 6.66666. Actually, if we took that further out, right, it's just this 6 just continues forever. So what we actually want here then to what we would want to do here for calculations, we probably want to write this out to at least 5 digits. Okay, and then when we put it in Blackboard, if I ask specifically for that in Blackboard, then we would shorten it down to 3 significant digits, which would be 6.7 amperes. But remember, for intermediate calculations, you want to make sure that you carry that out to 5 digits when you do your any other calculations. All right, so what we're going to do here then is we're going to go ahead and calculate for our R1 resistor. Okay, what is the voltage drop across R1? Well, using Ohm's law, we get that the voltage V1 is equal to the current I1 times the resistance R1. Right? So now we have I1 is the same as IT because it's in series. That's true. And so we have I1, which is going to be 6.6667 amperes times R1, which is simply 1 ohm, and therefore it's going to be 6.667 667 volts. And then again, if I'm going to put that into Blackboard now, if I try to put that into Blackboard, it's going to be 6.67 volts. And so that's going to be my Blackboard value for V1. Alright, so now if we want to calculate the value for resistor R2, okay, or the voltage across R2, it's going to be V2 is equal to the current through that resistor, which is I2, times the resistance R2. But again, I2, it's a series circuit, so these are all the same current. Okay, so I total is equal to I supply. It's a series circuit, so those are all the same. So now we have I2, which is again 6.6667. So you need to make sure you use the 5 digits when you're doing these kind of calculations here. Okay. And then that's times 2 ohms. Okay. And so if we try to calculate that, right, so we'll take this answer times 2 now, right, which gives us 13.3. And again, these 3's just kind of go out there forever, but we get 13.33333. I just wanted to show you that. So 13.333 volts. And so if we're going to put that into Blackboard, then it would be 13.3 volts. Okay. Again, it's going to be 13.3 volts there. All right, so now remember we had 20 volts supplied. So over here we got 6.67 volts, and over here we have 13.3 volts. So let's take a look there, and if we tried to add those up, okay, so if we took, you know, we can't have any more voltage than what was supplied, right? So we had 20 volts supplied, and I'm saying that I'm losing 6.67 volts here. Across V1 is 6.67 volts. And V2 is 13.3 volts. All right, and so let's just try to add these up. So if I try to add these up now, then I'm going to have 6.67. Whoa, that's a big font. We'll shrink that down a little bit here. All right, so we're going to have 6.67 volts plus 13.3. All right, and what I'm trying to show you here is the fact that if you try to add these up, right, we would have 19.97 volts. Okay. Well, my question is, what happened to the other 0.03 volts? All right. Where is that? And why I'm trying to show you this is the fact that why do we carry it out to 5 digits? So when you're trying to you know, what we're doing here is approximation values because we're rounding. We've rounded these up, and we're only doing 3 digits. So if you only do 3 digits, right, and you're ignoring this digit right here, then you might end up with something like 19.97 volts. And it's like, well, wait a minute, I had 20 volts over here. I've got 20 volts, not 19.9. And that's why we need to take the intermediate calculations out to 5 digits, because now if we take this out to 5 digits, so if we use the voltage of 5 digits, so we use 6.6667 volts, okay, and then we add to that 13.333 volts, okay, taking both of these out to 5 digits, not decimal places but digits. All right, so now notice here this 7, we're still kind of ignoring that. All right, but now we've got 19.999 volts, which is closer than 19.99. It's still off. All right, and in this case, if we round either one of those up, we would still end up with 20.0 volts when we round it up. But you see how, 19.999 is at least closer to the 20 than the 19.97. And so in this case, rounding up either one of them would have got us 20.0 at 3 digits. But sometimes that rounding will not get you the correct answer. In this case, I say even if I was to round this one up here, all right, this would still round up to 3 significant digits to 20.0 volts. Okay, so either one of these would still round up. In this case, either case rounded up to the exact same correct value of 20.0 volts to 3 significant digits. However, sometimes that rounding, if you round too soon, you would not get that. Okay, so, and actually, if we did the calculation, see, if we did the calculation of the voltage with that rounded value, it would actually throw us off. So you always want to take it out to 5 digits, as you're doing your calculations, and you always use at least 5 digits. I mean, if you keep it in your calculator, it'll keep even more than 5 digits. Calculators will keep out, depending on the calculator, it might keep out 15 to 20 or even more significant digits. So if you store the value within calculators, it will keep your values very accurate. But if you're writing them down somewhere and then you're going to use them again, make sure that you're using at least 5 digits there. Otherwise, your resulting answer might be off by a couple of decimal points.